Let's talk by Dr. Shuhei Miyashita.
Hi.
Hi.
Can you hear me?
Yes.
All right, then let me share my screen. All right, first of all, thank you for inviting me to this great opportunity. Hey, Fumi and Josie. My name is Shuhei Miyashita. I'm a lecturer at the University of Sheffield. Unfortunately, I'm recovering from a cold, so I may not speak well or I may not smart enough, but please bear with me. So in my talk, I would like to discuss how close can we bring bulk material to life. So our group is based in Sheffield. It's a city near Manchester. It's about an hour drive from Manchester, which has an international airport surrounded by a beautiful nature. So I lead Sheffield Micro Robotics Lab, SML, and then carry out researches including digital manufacturing, autonomous living materials, ingestible robots for biomedicine, and bio-inspired robot synthesis. The definition of life has remained as one of the biggest questions in science. Now, if you look at inside our body up to the molecular level, it's pretty much molecular synthesis. So we are molecular machines. As seen in the video, at elemental level, 20 types of amino acids interact with, attract to each other, and they eventually form higher dimensional structures spontaneously in the bottom up. You may remember in high school textbooks, they list the three characteristics that characterize life, namely self-reproduction, cell, and metabolism. Does that mean that if we endow artifacts with these aspects, will it naturally acquire capabilities that living systems have, such as growth or evolution? The manufacturing technology of building things bottom up, where a vast number of components interact with, attract to, and spontaneously assemble into a structure called self-assembly technology, has yet stayed as the major challenge in engineering. If we could develop, this one is a computer graphics, but if we could develop such a technology, it would not only widen the possibility of hands-free production of wide variety of things. For example, we just throw Lego blocks into a box and shake it. And what if we could obtain a car? That would be great. Or it would make such things resilient and reusable for sustainable production. And potentially, it would advance the manufacturability at microscale. So we are keen to know how close can we achieve the automated assembly in a bottom-up sense. One of our previous research projects was to develop a mini origami robot that can transform into different morphologies to acquire different functions. So here things start from one permanent magnet that can be electromagnetically actuated. So here you see a permanent magnet guided electromagnetically, which can hop onto this exoskeleton, origami exoskeleton, to acquire a first shape so that it can locomote. And now this first shape can now hop onto the second exoskeleton and put on this exoskeleton to transform into different morphologies. For example, in this demo, this minibot can now roll with 2 wheels. This minibot can now float on water as a boat, and this minibot can scale up its body size and so on and so on. And they can complete this process and repeat recursively by taking off this kind of origami exoskeleton just by jumping into water and then make this latching part dissolve. Although this project was initially pursued for the aim of utilizing such a transformable matter to be used inside the human body for micro-operation purpose, but it also raised some interesting philosophical questions, such as to what extent can materials evolve intelligence to exhibit functions? or at what point do materials begin to act with purpose. This minibot can also hop onto this self-folding origami exoskeleton to acquire two wings such that it can glide off from the stage, being escaped from magnetic control. Here in this video, we show self-assembly with 26 passive modules called Robotics, named after robotic tablets, self-assemble into two-dimensional stack beetle shapes. As you can see, the modules repeatedly collide with and attract to each other by the embedded magnets so that only complementary shapes can retain their bonds. The repetition of module collisions eventually leads to the parallel formation of two stack beetle shapes. Here in this video, you see self-assembly with 13 modules. Once all the connections are achieved, the assembled structure self-folds into a 3D shape, like origami, due to a temperature rise in the environment, in this case, contact with hot water. The 3D shape can be seamlessly actuated as a robot being guided by an external magnetic field, such that it can perform simple tasks such as picking and placing an object whose size is larger than the individual modules. This selective bonding mechanism, or smart glue, is great because it enables parallel self-assembly with heterogeneous modules, which had been quite difficult to achieve in this field. And it has essentially the same mechanism as jigsaw pieces, having only one other piece with a complementary shape, but not encoded in such an analog way, but in a more digital way with the combinations of concavities and convexities. This allows easy generation of component shapes computationally. For example, here you see there are 24 locations that can be shaped either into a concavity or convexity or flat. So simple math tells me the pattern that we can implement in this 24 location is 3 to the power of 24 times. That is billions, which is way redundant enough. For example, this tag beetle consists of 13 modules and having 13 connections. This means just having 13 types of connections, smart glue is enough to achieve the purpose. In practice, considering the symmetry of the geometry and the magnetic poles, we just need 5 smart glue patterns. There are two types of modules, modules that fold and modules that don't fold. So these are fold, and then this module doesn't fold. All folding modules are equipped with heat-sensitive shrinking film that induces self-folding. This is the first method combining self-assembly with self-folding and achieve a 3D structure formation in much faster speed than existing methods. Once a system self-folds, all the magnets had been arranged so that they face more or less the same direction, acting as a large single magnet from a distance, such that they can be seamlessly actuated by an external magnetic field such that it can walk away. Now let's think a bit more concretely. When one approaches to make a 3D structure, like a Stanford bunny, in an additive manner, not subtractive, but additive manner, typically one can start from the basic elements or random parts that can compose strings, which can compose planes, which can compose 3D structures, but not limited to. For example, if you agree that amino acids are the basic elements that compose our body, there are only 20 types of amino acids, and they start from parts form a protein, but protein directly jumps into a 3D structure by folding. And these folded 3D structures also, again, assemble and then form a higher order and higher dimensional structures and so on and so on. So they cyclically repeat this process. And of course, like Lego blocks, parts can directly form a 3D structure, but it is known to be quite difficult due to the large parametric search space. Now, our ultimate question is, if we would establish such a universal platform that can grow into any arbitrary designated 3D structure, would it naturally acquire a higher intellectual, higher order intelligence, let's say, as a consequence of emergence? Coming back to the initial question, what is life? What is the definition of life? These three aspects are mainly coined by biologists due to its observational perspectives. Physicists cite other aspects like entropy or energy and dissipative system, non-equilibrium. And it is also noteworthy to mention that there are over 300 definitions of life. Computer scientists, control people, and we roboticists cite these two keywords, adaptability or decision-making, quite more often in association with autonomy. Yeah, that's all on my talk. There is one opening PhD position in my lab. If you're interested in the position will start in September. Thank you for your attention.
Thank you very much for your great talk. It's very nice to know that the transformability is also another important aspect in the embodiment. This is wonderful. Thank you very much. So now we